Hi, I'm Parag Siddiq, a PhD candidate in industrial engineering at University of Louisville. I'm working with my co-advisor, Professor Kevin Gu and John Usher. Our research is about designing space-efficient parking lot for autonomous vehicles. I have laid out this poster in 4 columns. I introduce the research problem in the first column. Then in second and third, I talk about mathematical modeling and solution approach. And in the fourth column, I talk about our findings. Let's get started. Parking is a daily problem. Whether we are going to work or attending a ball game, the first thing that comes into our mind, where we are going to park. We need more parking spots. In a common parking lot, we get a maximum of 67% space utilization. Remaining space is devoted to driving lanes. Lanes must not be blocked for one simple reason. A blocked car might need to leave before the car that blocks it. However, the autonomous vehicles gives us an opportunity to overcome this problem and to achieve higher storage capacity. In this research, we explore how to achieve higher density in a parking lot utilizing self-parking and intelligent communication systems of autonomous vehicles. We consider parking lot as a rectangular grid with a single entry-exit point without presupposing traditional row and aisle structure. Cars take 2 cells to park, and cars can be parked horizontally or vertically. And cars are allowed to make these 3 moves inside the parking lot. We assume there is a central controller in the parking lot which can cooperate with the vehicles to schedule an entrance or exit. Let's talk about the model. We model the parking lot as a graph where a node represents a parking lot layout and an edge represents transition between 2 layouts. This is the graph we generate for a small parking lot. Observing the graph, we discover there exist 3 types of parking lot. This one shows a parking lot with maximum number of cars. Cars completely block each other, and cars can leave only in last in, first out sequence. Such a parking lot is commonly found in different events like a concert or a ball game. We call this design as limited egress design. Then the second type, where cars also block each other, but any car can leave by moving other cars. We call this design as complete egress. And finally, the third one is a traditional parking lot where there is no blocking. We have discovered these designs as we have initiated our research question without presupposing row and aisle structure. However, generating such graphs for larger grids is very hard computational problem. Therefore, we developed heuristic methods. We observed that if we bypass first few columns, we can park on all the rows. And then, bypassing first few rows, we can park on all the columns vertically. And then finally, there's a small area left out where we can apply our exact method to park car densely. We call this algorithm as puzzle-based parking algorithm. We then mathematically prove that we can achieve 100% parking density using this algorithm. You might be wondering how to retrieve a car from such a dense parking lot. Here is an example. From this layout, we retrieve the car number 8. The retrieval looks like a puzzle. That's why we have named such parking as puzzle-based parking. To perform vehicle retrieval in minimum number of moves, we use A-star search, which is a graph search algorithm widely used in robotics. Now let's talk about our findings. We know that we get 100% density in puzzle-based designs and 67% density in traditional designs. Therefore, we achieve 50% higher density in puzzle-based designs. For smaller parking lot, this gain can be as much as 80%. Density trades off with retrieval time. This figure shows a heat map of vehicle retrieval moves. Larger a parking lot, longer it takes to retrieve a vehicle. Especially these dark cars takes a long time to retrieve. In an 8x8 parking lot, if all the cars are Tesla Model S, then the car on the top right corner would take 10 minutes to retrieve. It is interesting to observe that if we reduce the density to 80%, retrieval times improves a lot. In summary, puzzle-based designs can achieve 100% density, but it is better to limit density to get a reasonable retrieval time. This research could be extended several ways. We have considered one entrance-exit point. Incorporating multiple entrance-exit would be an interesting extension of this research. Additionally, various car size will be another important direction for future research. Thank you very much. Feel free to ask any question.